This is section number 3, based on our flow chart for design of shaft, where we have to think about choice of materials. So in this case, when we start thinking about what material should we use for our shaft design, there are many considerations involving the performance. What kind of performance are we looking for? Is it like a high performance machine or equipment that we are going to design the shaft for? How we are going to manufacture this material, and some other commercial factors, including the cost, for example. Based on these considerations, this limits the choices for our materials that we can use. We have to use a material from the list that will be given on the next slide, and we have to use a ductile material as well. So there are some standard materials that you can use based on this table, and the values that are given here are approximate mechanical properties of these common shaft materials. So let's say this is a common shaft materials, and then these are the kind of materials that you can choose from. You see here, for example, we have carbon steel, we have low alloy steel, we have stainless steel, and these are the kind of the specifications or the standard that is used for each and every one, and it offers us the tensile strength. And you see here a range between 400 to 430, for example. So you can use the average value between these two if you were to go for anyone that has a range similar to this or that. It offers us the yield strength, where this is the value that we use for design. For the maximum shear stress theory, for example, it is we use this value or the next value, the yield shear strength, based on this table. So simply you can use this table or CS EDU pack. So you can again explore this option and try to find other materials as well, or other material properties. Next, as I said, due to those loads that are coming because we are transmitting the power between two shafts using gears in this case, so there are some deflections. Here, the figure shows some common cases of bending deflection only. We spoke about the twisting on previous slides, and how to calculate theta and how to compare it to some permissible value, which is 3 degrees per 1 meter of the shaft length. So on the left-hand side here, we have this very simple case where we have a shaft with a concentrated load in the middle F. So where you have here, reaction force R1 and R2. The reaction forces here, guys, is the location of the bearings now. So we need to think differently about this graph. So we have a shaft, and then if you just assume that this is your shaft, and then you have here one bearing on the left, another bearing on the right. So you have reaction forces here that is transmitted from, if we have let's say we have a gear here, and then the forces, if we are just two forces, the radial force and the tangential force, and these two forces, they just produce reaction forces here, R1 and R2. So based on the forces on the gear, so we can calculate the reaction forces here. So this is just a simple case where R1 and R2 are equal, and it is equal to the force divided by 2. And then the maximum deflection in the middle here is equal to FL cubed over 48 multiplied by the elastic modulus multiplied by the second moment of area. So this is the maximum deflection in the middle. So also it shows here the shear force diagram and the bending moment diagram. And this is quite important because actually if you see the maximum bending moment is FL over 4, and it is in the middle of the shaft. So the middle of the shaft for us now is a critical section. So if we were to design the shaft, if we have only a force in the middle, for example, so we find the maximum bending moment, and we say, okay, this is the critical shaft. This is the critical section of the shaft. We have to design the shaft at this particular point, and then we have to find our diameter or the minimum diameter of the shaft based on this value of the maximum bending moment. And also if there is torque, so the torque normally is uniform across the shaft. So at any point we have the same torque value. So we use the torque, for example, based on the power that is transmitted divided by omega. And then this is the maximum bending moment. And then we take these two values, go back to our failure criteria, either the first one, the distortion energy theory, or the second one, the maximum shear stress theory, and then substitute these values into those theories. And based on the yield strength that can be found from the previous table, based on the factor of safety that could be considered as 2 for general applications, we can find either the diameter, or we can find the factor of safety if you don't want to assume it. But remember that the factor of safety has to be always greater than 1 when you calculate it. On the right-hand side here, you have kind of the generic case if you have the force F, but the force F is not in the middle of the shaft. Again, we have reaction force on the left, R1, reaction force on the right, R2. And then you have these distances, A and B, and then the full length of the shaft is L. In this case, you can calculate the reaction force R1 and R2 based on the equilibrium equations, and then that you have studied in mechanics 1 and 2. And then you can also calculate the Y maximum, which is the maximum value of the deflection based on that. And also you see here at this location, you have the maximum bending moment, MMX. So this is now is the critical, or this is corresponding to the critical section that we have to design at. So we need to consider this maximum bending moment for design or for the failure criteria. Okay, compare your factored stresses with the material strength. So normally we have done this implicitly on the previous steps. Because actually we've just considered the strength of the material seal, we've just considered the factor of safety, we've compared the stresses that we've calculated, including sigma E, for example, in the von Mises theory, or sigma 1 minus sigma 2, the absolute value for the MSST. And then here for the distortion energy theory, and then we've compared these values together, and then we came up with 2 equations. One is to calculate the minimum diameter, and the second one to calculate the factor of safety. So we've done this implicitly when we were doing that. So the shaft specifications, eventually you are going to provide us with some engineering drawings for the shaft, for the bearings, for the gears, for all the other components. So we are using the British standard. It's called BS 8888. This is the standard that we are going to use for engineering drawing, either for the shaft or for any other component. So please just try to go to if you remember the resource list that is available on our Canvas page, and go to the, there is a relevant book there for engineering drawings, and this book is based on this standard. So if you wanted to draw a shaft, go back to the textbook, see how the shaft is drawn. If you wanted to draw, for example, a deep groove ball bearing, go back to the textbook and for the gears and all other components.